There are many optimization problems that have a local minimum. So if I draw, let's say, the contour of an objective here, you might find a solution here that isn't quite the lowest value. So we want to search for the lowest one, and that is going to be our global minimum. And this would be a local minimum. And you may have problems that have many local minima, but we want to try to design algorithms that can help us find the lowest or best value. And if you're maximizing, it would be the highest value. So let's talk about how we take a local minimizer and, okay, so we have a local minimizer. So there are many optimization algorithms that'll just find a local solution based on the KKT conditions, or other ways of using gradient descent. It's going to find a local value and get stuck there. Okay, now there are ways like simulated annealing or genetic algorithms or other algorithms that can help you find a global minimum. So here's, for example, a tree-structured Parson estimator optimization in action. So it shows how it searches, and then you also have a Bayesian estimator as well. Now this is for hyperparameter searching in machine learning. So you can see how it has Gaussian processes. It shows you the uncertainty there, and then it selects the one that has the maximum acquisition function. So in search of a global minimum. So there are many of these algorithms that we can use to try to find a global minimum, but these are generally going to be slow because you're basically just guessing and checking. So what I want to talk about today is a combined approach where we use a local minimizer to help us find a local solution, and then the global minimizer suggests initial conditions. So the initial conditions are then used to find a local minimum. And then we monitor this, all the local minima, to try to find the global minimum. Okay, so we're going to set that up with Python and run it in one of two ways. I was inspired by this question on Stack Overflow about this simple problem, so we're going to use this one. And also, as we go through it, thanks to Erwin for one of the solutions that I'll present here. Okay, so many different ways to search for a global minimum. In this case, it's hyperparameter search methods. We call hyperparameters because it's like these parameters that don't influence, aren't part of our original optimization problem, but they might be something like an initial guess value or initial conditions where you start searching. And you can either use a grid search, a random search, a Bayesian optimization like I showed in that graphic, a genetic algorithm, a gradient-based optimization, hyperband. So there are many other methods for performing this search. And some of these are going to be categorical as well, like solver options, which solver you select or which linear solver you use in a sequential quadratic programming solver. So many different options in the solver and also the initial guess values. Okay, so maybe I should say instead of initial conditions, I'll just say initial guesses. Okay, because initial conditions has almost a connotation in dynamics about where you start, and then you have a differential equation that has initial conditions. Okay, I guess what I'm saying is here we're talking about initial guesses for the optimizer. Okay, so let's come down here to this global optimization problem that I showed. And let's just first of all compute a local solution to this. Okay, so I'm going to do this with Gecko, but you could use other optimization packages as well. And I'll create 3 variables with a lower bound of 0. Just split those out, rename them as x1, x2, and x3. And there's our minimization. And then we have our equations, the equality constraint, and also the inequality constraint. So one of them is a linear equality and the other one is a quadratic inequality. And then I'll go ahead and solve it and then print the results. And there's our objective. Okay, so when I solve it, you could see that it finds one of the two local minima. It's the one that is the worst one. So it is not the global minimum. And in this case, we're using the solver IPOpt to solve it. So let's go and just set up multi-start with parallel threading. So in this space, let me just draw this in 2 dimensions. Let's say I just had x1 and x2, and let's say this were my optimal point right here. Maybe if I start in this region right here, then I find eventually that solution. And if I start over here, I might find the non-global minimum. So I'll just say that's global and that might be a local. So I want to multi-start. So I'm going to start at different places just using a grid search. So let's go ahead and set that up with multi-start with parallel threading. So it executes these simultaneously. So I'm going to do that with a threading package in Python. And I'll have Gecko there as well. We'll create the threading class and we'll initialize that. So every thread that you create, it'll have an ID and then our guess values. And then I'll create, just reduce the name to S for self, and self.id is going to be that ID. And then I'll have a model as well for a Gecko model and my initial guess values. Then I'll have an objective function. I haven't determined that yet, so I'll just give it, first of all, a none or a float NaN. All right, then I'll initialize the variables. I'll create my variables as I did before. And then also give them those initial guess values. Because when I initialize this, I'm going to know the initial guess values I want to use to try to solve that. All right, I'll define my x1, x2, and x3, and then define my equations as I did before. I just have to use s.m because now this is an object that's just unique to that thread. Then I'll define my objective as well, and then set solver option, and then initialize the thread. Okay, now this is when I run the thread. I'll print out that I'm running that application with the ID. Then I'll solve it, and then I'll retrieve the objective if I'm successful and store that in self.objective. Else, we'll put the objective equal to NaN. Then we'll clean it up just to remove any temporary run folders that are there, especially if we're running a lot of jobs. Okay, let's optimize at the mesh points now. Let's generate our initial guesses where we want to try to solve, find the solution. So again, this is the point where we're going to be finding, so guessing all of these values and then seeing how we approach these different objectives. Okay, and we'll do a grid throughout this whole space. This is going to be a 3-dimensional mesh. Okay, I'll have x1, x2, and x3, and just create a mesh grid of those. I'm going from 0 to 10 in increments of 3. All right, let's go ahead and create our array of threads, and we'll load these applications. So I only have 27 applications I'm solving. And you could have more. If you want to have a random number generator, for example, you could do that here instead of this grid method. Okay, I'll load the applications. All right, there are my initial guesses for each of those mesh points. And then I'll create a new thread with that ID and that initial guess. And then I'll increment the ID, just give each one a unique ID. And then I'll run the application simultaneously as multiple threads. So let's just have a maximum of 8 optimization problems that happen at once. Maybe you have a higher core processor and you might want to increase that to 16 or 32. All right, so I'm going to monitor the number of active threads, and I'll check for additional threads every 0.01 seconds. Okay, I think in a later version, I think it's active count, like that. Okay, but I'm just going to keep it that way, and then if it gives me an error, we'll switch it over. Okay, I'll start the thread and then check for completion. All right, there's our sleep timer. We're going to go for a maximum of 10 seconds and just get the best solution after 10 seconds. Now I'll also have a sleep time. It'll only check every second. Okay, so we're going to go with active count greater than or equal to 3. We'll sleep, we'll increment that timing, okay, and then look at the active count of threads that we have, and then we'll terminate after a certain maximum time. Okay, so if this is greater than 10, then we're going to break, and we'll initialize our array next to be able to collect all the objective values. So we're going to create one value for every dimension of x1. It's a 3-dimensional array, and we'll retrieve the objective results. Go through all of our IDs, and also keep track of which one is the best. So I'll just start off with 1 times 10 to the 10th, just to make sure that it initializes and the first best solution will be chosen. All right. I'm going to then look at my objective for each of the threads that were calculated. And if I am better than my best one, then I'm going to record that. There's my ID for my best one. There's my objective for my best one. Now I'll increment the ID and run this. Okay, so it's going to go ahead and run all of these. I guess it was more than the 27 that I anticipated. Okay, so a few more. But there you can see a number of active threads, and then it's going to terminate. Okay, I'll go ahead and work on this next one. Let's just get all the solutions. Okay, we'll print the objectives. All right, so these are, we started from those initial guesses that are the yellow squares there, or yellow X's. But these are the optimal, the local minima that it found. So you can see it found 936 for about half of them and 951 for about half of them as well. And then you can see some nada numbers where it didn't converge. Let's go ahead and get the best one. Okay, our best objective, and then also our solution X at that best objective. Okay, so it's 936, and then you can see 008. So that's better than the local solution that we had before. I'll scroll back up to it. There you can see it's 700 with an objective of 951. So we wanted to find the global solution, okay, which is that one, versus the local solution, which is this one. Okay, so this is just a multi-start method. There are also other ways to do this multi-start method, and one of the packages that I like using is Hyperopt, and I use this a lot for machine learning, for classification and regression. It can help you find hyperparameters that are optimal. Now, if we do a grid search, it can be very computationally expensive, especially when your number of variables and initial guesses really increases. So we want to be a little bit smarter about how we choose those and how we search for the global optimum. And in this case, we're going to use a tree-structured Parson estimator, or TPE for short. And we're going to use this fmin function within Hyperopt. Now, there are many different things that we can have for the choices. We can have categorical variables like hyperparameter choice, rand int for integers, or we can have a uniform or log uniform for continuous variables. So these are 3 that are built into Hyperopt. I'll show you how to use those and to be able to search for the solution. Okay, so we're going to use Gecko again, and Hyperopt will use fmin, the TPE, and HP. And we'll also have a status OK and a status fail. Now we want to define the search space for the hyperparameters. These are going to be our initial guesses. X1 is going to be a uniform distribution between 0 and 10. Steps 3, also X2 and X3. You're going to see how much less coding this takes than the one up above. Here's our objective. We're going to create a new gecko model with our array of X values, redefine the names of those, and then just give those our parameter. Okay, this becomes a dictionary on the input where it's sampling from this space right here. So instead of a grid search, it's going to use a TPE algorithm. Okay, there's our objective function and our two equations, and we'll just select the solver. We could have put maybe a choice in here for solver as well, and then given it the different solver options. But let's just go ahead and fix that for now at 1. Also have displays faults, debug faults so that it doesn't return an error if it can't find a solution. And then we'll record the objective function value. All right, our app status is going to be 1 if it's successful, and we'll return status OK. Else, we're going to return a status fail. And we imported those two right here from Hyperopt. Okay, and then we'll clean up that directory and then report our loss function. That's our objective function. The status, okay, which is status OK or status fail, and then also the X values. Okay, there's our best is going to be fmin. We include our objective, the space, and then the algorithm, as well as the maximum number of evaluations. So let's go ahead and run this. And you can see there are the trials. It's a nice progress bar there. So it was able to do about 12 trials per second, and it came up with our best loss of 936, which is the optimal solution. Let's go ahead and just print out the best. Okay, so it said that those were the initial guess values that led to that local optimum. Then let's go ahead and just evaluate those parameters best in this function right here to be able to return the objective and the optimal values. So we're going to run one more optimization problem. We'll get our solution status, we'll get our objective, and then the solution X. Okay, so solution status was okay. It found the global optimum, and there you can see the X values of the global optimum. So these were the initial guesses right here. These are the hyperparameters, or the values that we're trying to select to be able to find the global optimum. But then this is the solution with those initial guess values. Okay, so that's the tutorial on using a multi-start method or this hyperparameter optimization or Hyperopt. I just wanted to share with you there are also other global optimizers that are out there. And they work a little bit differently than just a multi-start method. You know, certain algorithms, let's say you have a minimum like this, and you find a local solution, it will then switch to a maximization, find a local maximum, and then continue descending down to a local minimum, knowing that a maximum has got to separate two local minima. And so it will take steps in that direction purposefully, okay, instead of just some type of random search, like a grid search or TPE or others. There are other algorithms that are implemented in global optimizing solvers to be able to help you find a global optimization solution a little bit faster. Okay, but this tutorial is all about using a local minimizer to help you find a global solution with a multi-start method or some other methods that are derived from hyperparameter search methods. Hope you've enjoyed this tutorial. There's additional tutorials here, and including the source code and the notebooks that are here in the design optimization for engineers course, and much more information here in terms of activities and lecture notes, as well as a book here if you would like to use this book to review some of the optimization methods that are out there.